Okay, so in this video we're going to be combining together the things we've been looking at over the last maybe 4 or 5 videos and looking at the idea of similar areas and similar volumes. And in my experience this is something that students generally do very poorly. So I guess, worth really trying to focus here on what's actually happening and working things out. So if we recall back to when we talked about similar figures and similar triangles, two figures are similar if one is an enlargement of the other. And the enlargement or scale factor gives the factor by which the side lengths are increased. So if we increase something by a scale factor of 2, we double all the side lengths. Now the key thing and the whole crux of what we're talking about throughout this video is that when we double all the side lengths, we don't also double the area. Something different happens to the area. And we don't also double the volume. Something even different again happens to the volume. Okay, so let's have a look at a situation. So here we've got two rectangles, rectangle A and rectangle B. Rectangle A has dimensions 2 by 4 and rectangle B has dimensions 6 by 12. Some simple maths allows us to see that those numbers have all been tripled. We can also calculate that scale factor of 3 by dividing corresponding lengths. So 12 divided by 4 gives us the scale factor of 3, and the fact that 6 divided by 2 also gives us a scale factor of 3 confirms that they are in fact similar figures. The whole thing has been enlarged by a factor of 3. So figure A has been enlarged by a scale factor of 3 to produce figure B, and that means the lengths have been multiplied by 3. So let's consider the scale factor between the areas. So the area of rectangle A is 2 by 4, which is 8 centimetres squared, and the area of rectangle B is 6 by 12, which is 72 centimetres squared. Now I hope we can also all see that 8 to 72 is not a scale factor of 3. Okay, so it's not been tripled. If it had been tripled, it would be area B would be 24. So it's actually a lot bigger than that. And we can work out that scale factor by dividing the values to see if we want to know what have I multiplied by. I want to know 8 multiplied by what gives me 72. That's the same as if I want to work out the what, I'm doing 72 divided by 8. Okay, and so that is 9. So the scale factor is 9. So when we enlarge by a scale factor of 3, that means multiplying all the lengths by 3. But the result of that is that all of the area ends up getting multiplied by 9. It's a 9 times bigger area. Okay, sorry, I'm still in trouble with my eraser. Okay, so when we enlarge the side lengths by a scale factor of 3, the area is enlarged by a factor of 9. Okay, so let's have a think about a more general situation. So let's look at a simple square with side lengths of 1 being enlarged to a bigger square with side lengths of k. So the scale factor is k. Okay, and that means the side lengths have been multiplied by k. So I'm going to start to refer to that as the linear scale factor or the length scale factor. And so if we want to compare the areas here, this shape obviously has an area of 1 centimetre squared, and this has an area of k squared centimetres squared. So we can see that the scale factor, if we've gone from 1 to k squared with the areas, we've multiplied the area by k squared. And that matches with what we saw back here. When the lengths were multiplied by 3, the areas were multiplied by 3 squared, which was 9. Okay, so we've got this general thing now which we can take to other problems. So the original area being multiplied by k squared gives the enlarged area. So we would talk about the area scale factor as being k squared. If the linear scale factor is k, then the area scale factor is k squared. Okay, so let's have a look at a couple of simple examples. A figure with area 20 centimetres squared is enlarged by a scale factor of k. So that is referring to the linear scale factor. The enlargement factor or the scale factor is just what you do to the side lengths. Okay, so that's telling us that k is 4. Find the area of the enlarged figure. Okay, so the original area was 20, so the enlarged area is going to be the original area, which was 20, multiplied by our scale factor squared. So that means that the area scale factor is 16. The linear scale factor is 4, the area scale factor is 16. So we're multiplying 20 by 16, and that's going to give us 3 320 centimetres squared. So if the original figure had an area of 20 centimetres squared, we enlarged all of the lengths by a factor of 4, and then we have an enlarged area of 320 centimetres squared, so 16 times bigger than the original area. Part B, a figure is enlarged by a factor of 5 to produce another figure with area 500 metres squared. Find the area of the original figure. Okay, so in Part A, we've been given the original area, okay, and we've been given K. So we worked out the enlarged area. In Part B, we have been given the enlarged area. Okay, so 500 is the enlarged area. And again, we've got the scale factor of 5, so that is K, which means K squared will be 25. Okay, so we know that the original area multiplied by the scale factor squared is equal to the enlarged area. Okay, so the original area times 25 equals the enlarged area, and so therefore the original area is going to be 500 divided by 25. So that's going to be 20. And units, meters squared in this problem. Okay, so if we took 20 and multiplied it by 5 squared, multiplied it by 25, we would get 500. Okay, so part C, find the value of x in the diagram opposite. Okay, so here we've been told that the area of this smaller, the area of this smaller triangle up here is 12 centimetres squared. The area of this bigger triangle is x centimetres squared. So we're trying to work out the larger area, the enlarged area. We've got the original area, so we need the scale factor. Now we've got some side lengths, so we should be able to work those out. But what we first need to know is that they are in fact similar shapes. And we do know that here because of the angles. We know that these angles are vertically opposite, and actually we probably just need that bit of information to confirm that they're similar. Okay, so if those are parallel, then that angle down there is the same as that angle there, and that one there is the same as that one there. Okay, so if we reorient the small triangle around to match the bigger one, okay, so the 12 centimetre squared triangle, again we want the dot at the top, we want that at the bottom there, and we want the cross at the bottom there. So it's 8 centimetres on that length between the, should have probably colour coded them, between the yellow and the pink angle. Okay, so if that's pink, oh sorry, I just did the pink one wrong off spot. Here, the dot is pink, and therefore that is yellow. Okay, so we've got them reoriented the same way around if I'm focusing on this triangle here and this one here. And so we know that they're similar, they have the same angles, therefore the side lengths are in the same proportion. So we can work out the scale factor, the linear scale factor. Okay, it's 48 divided by 8, which is 6. Okay, so this is 6 times bigger, the lengths are 6 times bigger, which means that the areas are 6 squared times bigger. Okay, so our enlarged area, which is x in this case, is going to be the original area, which was 12 multiplied by the scale factor squared, because we're enlarging the area. And so that is 12 times 36, which is 12 times 36, 432 units, centimetres squared. If the figures shown opposite are similar, so in part D we're being told they're similar, in part C we had to sort of establish that they were similar before we could use the properties of similarity. Find the value, so part D, these are similar figures, find the value of x. Okay, so x is an unknown length, but we've got both areas, so we can use the two areas to find what the scale factor is. Okay, so from area to area, we're essentially working out k squared. Okay, so we know that k squared, the linear scale factor squared, will be the scale factor between the areas, so that's 6.25 divided by 1, so that's 6.25. So that means the scale factor between the lengths is going to be the square root of 6.25. So let's do the square root of 6.25. 6.25, which is 2.5. So the lengths have been multiplied by 2.5, and so now we can work out that we're going to multiply the lengths by k, where k is, sorry, that's a 2.5. So we know that x is going to be 1.7 multiplied by 2.5. 1.7 multiplied by 2.5 is 4.25, and that's a length, and its units are meters. Okay, so if the lengths are multiplied by a scale factor of k, then the areas are multiplied by a scale factor of k squared. Okay, let's have a think about what happens to the volume when we enlarge a solid. So let's think about these two solids. We've got this smaller solid A with dimensions 1, 2, 3, and this larger solid B with dimensions 2, 4, 6. So we can see very clearly that we've multiplied all the side lengths by 2. Okay, we can see that 6 divided by 3 is 2, 2 divided by 1 is 2, 4 divided by 2 is also 2. The fact that all the lengths are in the same scale factor tells us that they're similar, and that the scale factor is 2. So let's consider the scale factor between the surface areas. So surface area is an area measure. We've just talked about the fact that areas are enlarged by a factor of k squared. So it should be, the surface area of B should be 4 times bigger than the surface area of A. So let's check that. So surface area of A, we're going to have 2 rectangles that are 2 by 1. So that's this bit here. We're going to have 2 rectangles that are 2 by 3. So that's the one on the front and the back. And then we are going to have, further 2 rectangles that are 1 by 3. So that's going to be those 2 rectangles there. Okay. Alright, so that calculation there, and if we work all that out, we find that cuboid A has a surface area of 22 centimeters squared. Surface area of B, cuboid B, there are 2 sides with dimensions 4 by 2, the top and the bottom. Okay. There are 2 sides with dimensions 4 by 6, that is the back and the front. Okay, so that's 4 by 6, and this is also 4 by 6. And then there are the 2 surfaces with dimensions 2 by 6, so that's these 2 sides here, either side. Okay, so if we calculate all that, we've got 2 lots of 4 by 2 plus 2 lots of 4 by 6 plus 2 lots of 2 by 6, and that works out to be 88 centimeters squared. So indeed, the area scale factor is 4. Okay, so we already knew that. And so hopefully we're probably coming to some sort of conclusion about what we think is happening between the volumes. So let's calculate the volume of these 2 solids. Volume of A is 1 by 2 by 3, which is 6 centimeters cubed. The volume of B is 2 by 4 by 6, which is 8 centimeters cubed. Okay, and so the volume scale factor is 48 divided by 6. We can see that that has been multiplied by a factor of 8. So 8 is 2 cubed. So the linear scale factor is 2. The area scale factor is 4, which is 2 squared, and the volume scale factor is 8, which is 2 cubed. Okay, and that's essentially because each of these numbers are 2 times bigger than these numbers. Okay, so if you think about it, if the original calculation was 1 by 2 by 3, well, this thing is actually 2 lots of 1 times 2 lots of 2 times 2 lots of 3. So we've essentially multiplied by 2 3 times, hence 2 cubed times larger. Okay, 2 times 2 times 2. Alright, so we can see if we enlarge the side lengths by a factor of 2, so if k equals 2, we enlarge the surface area by a factor of 4, k squared equals 4, and we enlarge the, that should say volume, and the volume is enlarged by a factor of 8. So k cubed is equal to 8. Okay. So scale factors between lengths is k, the scale factors between areas is k squared, and the scale factors between volumes is k cubed, and we can confirm that here. So if we have that nice simple cube 1 by 1 by 1 by 1, and an enlarged cube k by k by k by k, so the enlargement factor, the factor by which the lengths have been enlarged, is k, so it's the linear scale factor. We could then calculate the surface area of each of these solids. This has 6 surfaces that are all 1 by 1, so that is 6 centimeters squared. This has 6 surfaces that are all k by k, so it's 6k squared centimeters squared. So to get from 6 to 6k squared, we've clearly multiplied by, k squared. So the area scale factor is k squared. And if we calculate, so that applies to areas and surface areas, it's the same measure. So the original surface area multiplied by k squared, the enlargement factor squared, gives the enlarged surface area. And then the volume scale factor, well, the volume of this smaller cube would be 1 by 1 by 1, so 1 centimetre cubed. The volume of this larger cubed is k by k by k, so k cubed centimetres cubed. And so to get from 1 to k cubed, we've multiplied by k cubed. Okay, so the volume scale factor is k cubed. So the original volume multiplied by k cubed, that is the linear scale factor cubed, is equal to the enlarged volume. Right, so let's work on some problems here. A solid with a surface area of 100 centimetres squared and a volume of 60 centimetres cubed is enlarged by a scale factor of 3. Okay, so that's the linear or length scale factor unless we're told differently. Find the surface area and the volume of the enlarged figure. Okay, so the enlarged surface area is going to be the original surface area, which was 100 centimetres squared, multiplied by the area scale factor, which is k squared, so 3 squared. So that's 100 times 9, and so that is 900 centimetres squared, the enlarged surface area. And the enlarged volume, enlarged volume is going to be the original volume, which was 60 centimetres cubed, multiplied by the volume scale factor, which is k cubed, so that is 3 cubed. So it is 60 multiplied by 3 cubed is 27. So 60 times 27 is 1,620, and its volume, so that is centimetres cubed. A solid is enlarged by a factor of 5, so that's the linear scale factor, k is 5, so that its volume is 1,000 centimetres cubed. So that's the enlarged volume. A solid is enlarged so that its volume is going to be, it becomes the enlarged volume is 1,000 centimetres cubed. Find the volume of the original. Okay, so we've got this relationship between original volume and enlarged volume and k, and in this problem we know the enlarged volume, we know k, and it's the original that we're trying to find. Okay, so we know that the original volume multiplied by k cubed, so 5 cubed, equals the enlarged volume, which in this case is 1,000. Okay, so that means the original volume multiplied by, now 5 cubed is 125, you can confirm that with your CAS if you need to. So original volume multiplied by 125 gives 1,000. So that means that the original volume is going to be 1,000 divided by 125. If you need your CAS to solve this for you, if you're not very comfortable with the algebra, fine, k times 125 equals 1,000, or x times 125 equals 1,000, and solve for x. The original volume is 8. If you're happy to work out that you need to divide 1,000 by 125 by hand, then you don't need to solve. You can just type in 1,000, I did 100, apologies, 1,000 over 125, and you will need to press Control Enter to get a decimal if it's a decimal, but this is a nice exact answer. So that is 8, and the volume units are centimetres cubed. So the original volume is 8 centimetres cubed. We enlarge all the side lengths by a factor of 5, which means we enlarge the volume by a factor of 125, and so the enlarged volume is 8 times 125, which is 1,000. Okay, part C, the diagram opposite shows similar figures, so we know that they're similar. Find the value of x. Okay, so x is the surface area of the larger solid. Okay, so we're going to need to know about k squared to get from the smaller surface area to the largest surface area. So we're going to use these lengths to find what k is. Okay, so k is 21 on 14, which is 3 on 2, so that's 1.5. Okay, so the lengths have been enlarged by a scale factor of 1.5, and so that means that the areas have been enlarged by a scale factor of 1.5 squared. Okay, so we know the enlarged area, which is x, is going to be equal to the original area, which is 100, multiplied by the area scale factor, which is k squared, so 1.5 squared. So 100 times 1.5 squared is 225. That's an area, and the units are millimetres squared. Okay, part D, calculate the volume of the small cone. So we've got the areas of these two surfaces, 45 and 5, and we've got the volume of the larger cone. Okay, so maybe let's separate it out. So we've got the small cone and we've got the large cone. Okay, so we know that that area is 5 centimeters squared, and we know that that area is 45. So we can work out what the scale factor between the areas is. Okay, so to get from that area to that area, it's an area scale factor, so it's k squared is 45 over 5, which is 9. Okay, so the areas have been enlarged by 9, which means the area scale factor k squared is 9. So from that, we can work out that if k squared is 9, that means that k is the square root of 9, so 3. Okay, so the lengths have all been tripled. And so now, so we've been given the area scale factor, we take the square root to get back to the linear scale factor, so that then we can cube k, so 3 cubed, to find that the volume scale factor is 27. Okay, and so we've got the volume of the larger cone. Okay, so the volume is 270 centimeters cubed, and we want to know what this volume is. Okay, and so we know that from the smaller volume, so let's call this one x. Okay, from the smaller volume to the larger volume, we're multiplying by that volume scale factor, which is 27. Okay, so we know that x, the smaller volume multiplied by 27, gives the larger volume, which is 270. And so we can solve that by dividing both sides by 27, and we find that x has to be 10. X being the smaller volume. Okay, so we introduced x into the problem. The question didn't ask us to find x. It's calculate the volume of the small cone. Okay, so the volume of the small cone is equal to 10, and the units of volume here are centimeters cubed. As always, if you're not comfortable solving that equation by hand, solve x times 27 equals 270 for x, and your calc will do it for you. Okay, exercise 17G, looking at similar areas and similar volumes.